As an introduction, we know that there are many efforts from all types of community to alert the whole population about the dangers of pollution. One of them is by assessing the water quality to help save the river. So there are many elements that can be considered when doing the water quality assessment, such as the level of dissolved oxygen and the presence of chemical substances, and so on. So in this project, we focus on to observe the pollution of the river water through the biochemical oxygen demand (BOD) and the concentration of dissolved oxygen. And we want to determine the system of the linear of water quality indexes using Travis transform and to solve the differential equation problem using Python.
About dynamic modeling and control of dissolved oxygen DO and biochemical oxygen demand BOD, which involve tidal river system that consists of ordinary differential equation model for DO and BOD in order to maintain the aquatic life and the quality of the river. Quality management is to determine how organic matter affects the concentration of DO, and BOD is to measure the amount of suitable substances in water sample. We also provide manual calculation for the model using Laplace transform. The model is used to maintain specific levels of instinct DO in both single and multiple rich river system.
So this is our model. Our model is taken from the Young and Beck 1974, which the distribution is as given. The first equation is dx1t over dt equals to negative a1 plus QE over Vm times x1t minus a2 times x2t plus q over Vm times c times t minus td plus a1 times cs minus db. And the second equation is dx2t over dt equals to negative a2 plus a3 plus QE over Vm times x2t plus q over Vm times l times t minus td plus la plus QE over Vm times u. The initial condition is x1 0 equals to 8, x2 0 equals to 12, a1 equal to 0.2, a2 equal to 0.32, a3 equal to 0, t equal to 0, td equals to 1, l equals to 3, la equal to 0, u equals to 10, db equal to 0.1, c equals to 9, cs equal to 10, q over Vm equal to 0.9, and QE over Vm equal to 0.1. This model is a simple ordinary differential equation ODE model for the DO-BOD interaction in a ridge of the river system. The model is derived from the two-component mass balance over the continuous tank rectus CSTR section with the delay variable relationship LT minus TD and the CT minus TD represented by L prime T and the C prime T respectively. It is assumed that Vm is a constant and overall mass balance permitted the simplification of a uniform flow rate Q plus QE throughout the ridge. Pure time delay TD is required to allow the transportation effect that will effectively be absorbed into the lag properties associated with the basic CSTR model.
Result in discussion, so the LVP is given by these two equations, and initial condition is x10 equals to 8 and x20 equals to 12. Next, we need to substitute all the values of the parameters into these two equations and we get equation 1 and equation 2. Next, we need to apply Laplace transformation on equation 1 and equation 2. We need to apply both for left hand side and right hand side. Then we get the second line, and after we got the second line, we need to substitute with the initial condition and we simplify until we get x1 and x2. Next, we need to perform inverse Laplace on equation 1. But before that, we need to substitute x2 into this equation and simplify it until we get x1t equals to inverse Laplace of this. Then we need to find the partial fraction and solve for equation 1. Then we find a, b, c, and d. After we find a, b, c, and d, we can just perform inverse Laplace and we got the final solution for x1. Next, we need to perform inverse Laplace on equation 2. So x2t equals to inverse Laplace of this. Then we need to find the partial fraction and solve for equation 2. Since like before, we find for a, b, and c, and we perform inverse Laplace and we get the final answer for x2. The edit solution. So here is all the variable and parameters and equations. So here we solve for x2 and we substitute here to find for x1, and this is the final answer for x1 and x2. So this is the result. So for this question, manual solution and computer edit solution give the same value, thus we can say that the calculation and solutions are true. Based on DO graph, which is the x1 graph, the highest value of dissolved oxygen is 40 mg per liter. Next, for BOD graph, which is the x2 graph, the highest value of BOD is 40 mg per liter, which means that the river water is severely polluted.
The normal value for DO should be around 6.5 to 8 mg per liter and BOD should be around 2 to 8 mg per liter. Based on the result above, the value for both DO and BOD is increasing at particular time. It is good to have high DO because organisms in river can survive, and it is not good for BOD to have high level because it will be less oxygen and the organism will die.
For recommendation, the constant values assigned must be suitable to the weather because it can easily affect the balance of BOD and DO. The second one is the eventual viability of automatic water quality control on a river system will depend on the results of a thorough benefit cost analysis of such innovations. And the third one is to have a good water quality. People must take actions to help preserve the river water by reducing the usage of substances that are impossible to decompose naturally. Thank you.